Hey, calculus students. So as I told you, I am at a training at the district office, learning all about assessments and proper assessment techniques. So yeah, it should be a good time. Unfortunately, I will miss being in class with you guys today. But what I did want to do is I didn't want us to get behind or have you guys feel like I left you behind. So I'm spending my Sunday here recording all of my lessons for all three of my different classes. I teach in Algebra 2, I teach two sections of BC Calculus, I teach multivariable calculus. But anyway, so I'm spending my Sunday here recording my lessons so that we're all on the same page still when I get back. And this is pretty quick. It is a review. And basically what I want to talk about is using derivatives to find local minimums and maximums. And we will talk a little bit about global minimums and maximums as well. So that's another little bit of an addendum. One thing I should remind you guys, remember that since this is a video, your teacher can pause this video at any time. He or she can rewind it. You guys can turn the sound off if you're tired of listening to me. You got all sorts of options. So make sure that you're not shy. Make sure to raise your hand and ask if volume needs to be changed or if you missed something and you'd like the video to be paused. Anyway, so first problem we're going to look at. We are going to take a polynomial equation, 2x cubed plus 9x squared minus 24x minus 30, and we're going to find all the global and local extreme points on the interval from -5 to 4. So that's where we're going to be looking for this one. The first thing we have to do, guys, is find all of the critical values. And usually what you guys think of doing, you usually think of this as just taking f prime of x and setting it equal to 0. And those are your critical points. Now, for the most part, that is true. But technically speaking, extreme values can occur any place where the derivative is equal to 0. Those are critical values. Anywhere the derivative is undefined, and also at endpoints. For a quick example of that, if you only used the technique of setting the derivative equal to 0 in solving, and those were your only critical points, you would miss extreme values. For example, this is both the local and the global minimum for this particular absolute value equation. I guess it would be like y equals absolute value of x minus 2. There's a local min at x equals 2. In fact, it's a global minimum because it's the lowest point that occurs anywhere on this graph. But if you were to try to take f prime of x and set it equal to 0 and solve, x equals 2 would not pop up. So you can only get this as a point where the derivative is undefined. Anyway, sorry about that quick tangent that I went on. Just important to have this in your notes because it's something that will come up throughout the year. Don't just set the derivative equal to 0. Also, remember that you have to look at endpoints and undefined points where the derivative is undefined. In any case, as with any Calc A problem, you always start by taking the derivative. So we're going to say f prime of x is equal to 6x squared plus 18x minus 24. You guys are great at taking these derivatives of polynomials, so that we don't need to talk about that too much. And the first critical values we're going to look for are the ones that you get by setting the derivative equal to 0 and solving. So I purposely set up this problem to be one that is pretty darn easy to factor and solve. So 6x squared plus 18x minus 24 equals 0. There's a greatest common factor here that we can factor out. It's a factor of 6. And we're left with a much simpler degree 2 polynomial here, x squared plus 3x minus 4. That factors as x plus 4 times x plus, this factors as x plus 4 times x minus 1. That's set equal to 0. We get two x values, -4 and 1. Okay, now if I were in class, I would ask you guys, are these necessarily x values where we have extreme values? Do these necessarily correspond to local minimums or maximums? The answer that I would be looking for if I was able to ask that is no. These are called critical values. Now, critical values are candidates for where you can have local maximums and minimums, but they are not necessarily descriptive of where you have a local maximum or minimum. I could think of an example of that. Think of this function right here. At this point, we have a horizontal tangent at this purple point that I just put down. It's a critical value. It's where f prime of x is equal to 0. But if you inspect this graph a little bit further, this is neither a minimum nor a maximum. It is a point of inflection, but it's not an extreme value in the sense that we're looking for extreme values. So, keep that in mind. These are critical values, but until we test them, until we work with those critical values, we really don't know much about whether it's a minimum or maximum at -4 and at x equals 1. Now, you guys made line charts last year, so we can make a line chart. We look at the derivative, and that will help us describe what's happening to the function. So f prime of x, what you're going to do is you're going to test values between -5 and -4, between -4 and 1, and between 1 and 4. We're testing intervals. Essentially what we're doing is on this closed interval right here of -5 to 4, we're going to put our critical values on that we found between. So we've got our 4 critical values. We're going to look at these intervals. Is f prime of x positive? Is f prime of x negative? Is f prime of x 0 on these 3 intervals? So I'm going to test like f prime of -4.5. You just do that in your calculator. F prime of 0. F prime of, we could pick any number between 1 and 4. Probably 2 is the easiest one to plug in there. Doesn't really matter though. So you can either use your calculator, or if you can do it in your head, because this derivative is easy to work with, you can do that. Either way, you're going to figure out that between -5 and -4, that the derivative is positive. And once again, if I were in class, I'd ask someone to raise their hand and tell me if the derivative is positive, does that mean that the function is increasing, decreasing, or neither? And the answer to that, of course, is increasing. The function is increasing on the interval from -5 to -4. Likewise, when we test f of 0, we're going to discover that the function, the derivative of the function is negative. And if I were here, I'd ask someone to raise their hand and tell me if the derivative of a function is negative on an interval, is the function increasing, decreasing, or neither on that interval? And of course, you guys are all calculus superstars already, so you know that the function is decreasing on that interval. And then finally, from 1 to 4, the function is increasing on that interval because the derivative is positive on the interval from 1 to 4. Okay, now, by the way, these line charts are really nice. They're a really good way to organize your work. Make sure that you don't use them as your sole means of explaining things on the AP test. On the AP test, they don't know what these line charts are. These are something we use at FREMD, but not every school will use them. When we're going to describe where we have minimums and maximums, we're going to describe it in a sentence. So if you ever have any one of these like max-min problems on an AP problem, make sure that you don't just do this line chart and stop there. There's going to be a little bit more explaining we're going to have to do. So the next question that I would have asked you guys, and you could just think about this in your head instead of answering me, if a function changes from increasing to decreasing, then what happens in between? At -4 here, what is x equals -4, what's happening here? And you could kind of think about this as the function's increasing, then it's decreasing. We're going to have a maximum here. And then the function, once again, now the function is going to go from decreasing, the function's going down, it's decreasing, and then again, it's increasing. And so if we go from a negative derivative to a positive derivative, or the function is decreasing and changes to increasing, we're going to have a minimum right there. So we've figured out where we have a local max and a local min. Of course, just because we have a local maximum at x equals -4 or a local minimum at x equals 1, globally we still have a little bit more legwork to do to figure out what exactly is happening. So you're going to make a table, and you're testing for basically your global maximums and your global minimums now. You know it at -4, x equals -4, and x equals 1, we have local extrema there. That means in a small neighborhood, in some area, we're at the top of a little hill. I don't know if this is the tallest hill on our entire graph, but it is a hill that we do encounter. Okay, what we're going to do is we're going to find these y values. And you find those y values simply by plugging these numbers back into our original equation. So, you know, you guys can do the legwork for that yourselves. You don't need me for that. You just use your calculator. But when we input an x value of -5 into the function outputs a y value of 65. When we input -4 into the function, it outputs 82. We have a y value of 82. When we input 1, we output -43. And when we input 4, we output 146. Now these are big numbers. That's fine. I do have a graph on the next page. So if this were the AP test, here's the sort of thing you would want to say. You would say, for example, because the derivative changes from positive to negative at x equals -4, we know the graph has a local maximum at x equals -4. The coordinates of this point are -4, 82. Or you could probably shorten things a little bit by saying the graph has a local maximum at the point -4, 82. This is the sort of thing they're going to be looking for on the AP test. They want you to describe that because the derivative changes from positive to negative, or because the function changes from increasing to decreasing, that you have a local maximum at a given point. And if they ask for the maximum value, that maximum value is 82. If they ask for the x value of that of the maximum, it's at -4. The safest way to do this is just say that you have a local maximum at these coordinates and give both coordinates. Okay, so what we discovered on the previous slide is that we have a local maximum at -4, 82 or whatever it was, a local maximum at x equals 1, and then remember we have to include our endpoints when we're looking at things globally. And on a global scale, oops, sorry about that. On a global scale, we have a global maximum at x equals 4. The coordinates of that point are 4, I believe it was 146. We have both a local and a global minimum at x equals 1, and the coordinates of that point were 1, -43. And finally, we have a local maximum at x equals -4, and I think it was -4, 82, but I'll just double check that. And then this last point right here that we didn't talk about, this -5, that's nothing. It's neither a, well, I guess you could maybe describe it as a local minimum on this particular interval from -5 to 4, but we don't really have to describe endpoints as local minima. They're really just candidates as global minima in our case, global minimums and maximums. Okay, so we found everything that they're looking for. Now, this like line chart thing we did, this reasoning we did here that I'm drawing arrows pointing to, or I guess we did the same thing in a sentence on the previous page. That's how you do it on the AP test. This is called the first derivative test. We're using the first derivative to describe the behavior of a function. First derivative test is a great way to determine if you have local maximums or minimums at given points. However, there's another test out there. It's called the second derivative test, and I'm going to show you how the second derivative test works because it's useful throughout the school year. It's useful on the AP test. It might be useful on some problems you're going to see in the very near future. So you did learn about this, but it's been a little while. This is the same problem again, so don't feel like you have to write all of this junk all over again. We already did that. We're just going to do the same problem again using the second derivative to identify maximums and minimums, local maximums and minimums. Here's what you do. You've taken the first derivative to find your critical values. Now we're going to take the second derivative to determine if these critical values describe local maximums or local minimums. So we have f double prime of x is equal to 12x plus 18. When we're working with these polynomial equations, it's nice and easy to take further and further derivatives. Now what you're going to do is you're going to make a line chart again. But notice this line chart does not have the first derivative. It has the second derivative because we're doing the second derivative test. Now, the reason that the second derivative test is nice, there's actually a couple reasons. When you're talking about implicit differentiation and some uglier equations, sometimes the second derivative test is a lot easier than and more manageable than this line chart business. But the other thing is, with the first derivative test, we had to test the number on 1, 2, 3 intervals. We had to test a value between -5 and -4, another value between -4 and 1, and a third value between 1 and 4. For the second derivative test, you're testing your critical values directly. We're going to plug -4 and 1 into the second derivative. And what you're going to find is when you find f double prime of -4, you're going to get a negative number. Go ahead and write a negative there. Likewise, when we plug 1 into the second derivative, when we find f double prime of 1, that's going to be positive. Now that's actually going to tell us how the function is behaving, and here's how it works. Remember that the second derivative describes concavity. And so if the second derivative is negative at a point, then that means that the graph is, try to think about it in your head, is it concave up or concave down? The answer is concave down. Wish I was there to ask that, but the graph is concave down. Well, if the first derivative is equal to 0 and the second derivative is negative, that's going to imply that you have a local, what does this look like, a maximum or a minimum? It's a local maximum. Okay, same sort of idea right here. F double prime of 1, that's going to be positive, so that means our graph is concave up. Okay, well, if our graph is concave up, look at this little point at the bottom. This looks like a minimum. So if f prime of x is equal to 0 at a point, and the second derivative is positive, that implies we have a local minimum at our x value. That's the second derivative test. The benefits of it, you're plugging in fewer numbers back into an equation, and in fact, many times the second derivative is a simpler equation than the first derivative, and so not only are you plugging in fewer numbers, one fewer number, but you're plugging those fewer numbers into a simpler equation. So I think the second derivative test is a good thing for you guys to remember. Now, pretend we still had to identify those local maxes and mins, even though we just did it on the previous slide. If this were the AP test, you would not just draw this line chart picture. This line chart picture is insufficient. You would need to say that since... I'm having a hard time spelling today, guys. I'm sorry about that. Since f prime of negative 4 is equal to 0, and f double prime of negative 4 is less than 0, we have a local maximum at the point negative 4 comma 82. Now you don't want to just say at x equals negative 4 necessarily. They might be looking for this 82. They might say what is the maximum value, or what is the locally maximum value at x equals negative 4, and you need to give them that 82. So writing the answer this way, giving the whole set of coordinates, not just the x coordinate, is probably a better way to write it. And there's that table again. So once you do the second derivative test, you still need to test your endpoints. The second derivative test is good for those critical values that you get the first derivative equal to 0. Not so good for finding global minimums or maximums. You need to test your endpoints for that. So. All right, I hope that was a helpful set of examples there, the big long example one. I do have one more to look at quickly. Implicit differentiation, I'm going to get that into the mix, and then we're going to be done for the day. So I'm going to start out with a circle with coordinates, with rectangular coordinates described by the equation x minus 1 quantity squared plus y minus 2 quantity squared is equal to 36. And we're going to try to find the maximum point on the circle. Now I know that like 35 to 70% of you guys right now, I'm just making those numbers up, but a good chunk of you guys right now are thinking, I don't need calculus to find the maximum point on a circle. I know how to graph circles. I can find maximum points on circles very easily. In this case, it's just going to be 6 units above the center of the circle. Center of the circle is 1, 2. Radius is equal to 6. 6 units above this y coordinate of 2 is 8. I already know that the maximum point on the circle is 1, 8. That's awesome if you already reasoned through that and figured out the answer without doing any calculus. We're going to do calculus on this, not because it's necessary, but this is a good example for some harder problems. It's going to lay the groundwork for some harder problems you guys are going to see very soon. So. If we're going to get y prime equal to 0, we need to implicitly differentiate. By the way, remember y prime equal to 0, that's the same thing as f prime of x is equal to 0 or dy dx is equal to 0. We have those 3 ways of describing the derivative. I'm using y prime because when we're doing implicit differentiation, that's the method that kind of pops out at us, right? Y prime is a good notation. So our implicitly differentiated circle formula is going to be 2 times the quantity x minus 1 plus 2 times the quantity y minus 2, and then after that a y prime is equal to 0. If you're wondering where this y prime came from, remember when we do the power rule and get that 2 out there as a coefficient at the beginning, we also have to multiply by the derivative of the inside. The derivative of y is y prime. That doesn't really affect us for this first part, so there's nothing... When we use chain rule here, there's nothing that pops out from the x minus 1 quantity squared, just the y minus 2 quantity squared. Okay, and then we could get y prime alone on one side of this equation. And once you do that little bit of algebraic legwork, you get y prime is equal to 1 minus x divided by the quantity y minus 2. That's our dy dx, that's our f prime of x, if you will. Set that equal to 0. Really, only this numerator matters when we set that whole thing equal to 0. That numerator tells us that x equals 1. That denominator of y minus 2 does not affect us solving this equation. So There it is. X is equal to 1. When x is equal to 1, y is equal to -4 or 8. And remember, I kind of already gave away the ending here. I kind of spoiled the problem. I told you that this maximum point is going to be at 1, 8. Now, if I were in class, I would ask you guys, what is the 1, -4? What does that represent? And I'm guessing that someone would very quickly raise their hand and tell me the minimum point. But let's continue working through this. Let's not stop here. Okay, so y double prime. I'm going to do the second derivative test. So I'm going to find the second derivative. And let's see. So I get y double prime is y minus 2 times -1 minus 1 minus x times that quantity times y prime for y minus 2 quantity squared. Yeah, that checks out for me. All I did, guys, is I took y prime and I did ho d high minus high d ho over ho ho. Remember, we're taking the derivative of high over ho. So that's where that comes from. So then I think probably a good thing to do is to replace that y prime with the original equation for y prime, 1 minus x over y minus 2. And then I think if I just multiply all three of these terms by y minus 2, it gets the equation in a much nicer form. I think it's y minus 2 quantity squared, still times that -1. And then it looks like I have 2 copies of 1 minus x. And then the y minus 2 cancels there. And then, by the way, if you don't see what I'm doing here, I'm multiplying the top and the bottom by y minus 2. And then in the denominator, let's see, y minus 2 times y minus 2, y minus 2 quantity cubed. Yeah, that looks great. And then a little bit of housekeeping here. I'm going to factor out a negative. And actually, so there's that negative right there. Actually, 1 minus x times 1 minus x, that's the same thing as x minus 1 quantity squared. So this is probably the nicest way to write our second derivative. You don't want to multiply that out, it'll be ugly, so just leave it in this kind of semi-factored form. And now that we have a nice form for the second derivative, the reason for doing that is we already know that 1, 8 is going to be our maximum point. But to prove it, to do like an AP test level of rigor, what we need to do is take this 1, 8, put it into the second derivative, and now think about what you want the second derivative to be. Think about if you want it to be positive or if you want it to be negative. Another way of saying that is think about whether you want the graph to be concave up or concave down at the point 1, 8. Now the answer to that question is that we, if I was able to ask that question, we would want the graph to be concave down, so that we have a maximum at 1, 8. So we're going to do the second derivative test to verify that. By the way, here's a nice picture of this circle. X minus 1 quantity squared plus y minus 2 quantity squared is equal to 36. Centered at 1, 2, radius of 6. Here's our second derivative, so we can do our second derivative test. We're going to take 1, 8. We're going to plug it on in. At 1, 8, the second derivative, let's see, this quantity right here is positive. This quantity right here is 0. This quantity down here is positive, but there's a negative out front. So this y double prime is negative at 1, 8. So there's a maximum there. Basically what we did is we proved that at 1, 8, y prime is equal to 0 and y double prime is less than 0. So there's a maximum at the point 1, 8. On the AP test, as long as you write this out more in plain English rather than using so many symbols, this would be an acceptable way to prove that 1, 8 is a maximum on the circle. The derivative here is 0, and the second derivative is negative. That is, it's concave down at the point 1, 8. So therefore, this is our maximum. And then down here, you could do the same thing to prove that 1 comma negative 4 is a minimum. One interesting thing, when I said there's a maximum here, we can actually show this is both a global and a local maximum for this particular problem. This is the highest point on the whole graph, and in a small little area, this is the top of the hill. So global and local. Okay, guys, I hope you enjoyed this this little video cast. I hope it helps you out with some problems you're going to be working on today, and I will see you all tomorrow, okay? Remember that you can ask your teacher to rewind this or pause this if you need to go back and look at anything else from a previous example. So, and I'll try to put this on YouTube as well, maybe maybe Monday night. So.